We're going to look at waves and sound, and you're going to be using a graphing program called Desmos at the same time. And I have it located here, desmos.com/calculator. However, you may have trouble following my description and Desmos simultaneously, and you'll be pausing the video. You might want to use just the slideshow itself. So there's a quick way of being able to do this that I would like to show you. I'm going to grab my Waves and Sound tab here and just click and hold and drag. And now I've separated it to its own screen. And I will minimize it a bit or make it smaller and drag it all the way to the right, and it will expand and hold half the screen. And at this point, I can go to the other screen here and drag the whole group of tabs down. I don't need to separate them. And I just drag that over to the right. And now I've got two half screens. So very carefully, if I slide it over here, I can't swing to the left because I have two monitors set up. And so you can do it by dragging far to the left if you have a single monitor. And now I can go into Desmos, and at the same time you can have the two open. You don't need to make it 50-50 either. You might find it's easier to do something like that or split top and bottom. But what you will find is it will be a lot easier to do it that way, or play it on your cell phone instead and have your desktop computer for Desmos. Now let's begin the lesson itself. Waves and sound. A mechanical wave is a periodic energy disturbance that passes through a medium or material, but is not the material itself. Now, it doesn't have to be a regular repeating or periodic wave. A single pulse can happen as well, and this is called a soliton, which sounds pretty darn cool. We're looking at what we call sinusoidal waves, and a sinusoidal wave is exactly like the sine curve in mathematics. The one here is a simple sine wave, and here's like a decaying sine wave I did on Desmos. Here is a superimposed sine wave. The fact is it's waving like ripples on water, and that's a sinusoidal wave. We want to locate what a single wave is. How do we decide what one wave is out of this entire series? And what we look for is the start of a wave, the peak, the trough, and then it goes back to zero. This is where it started, and this is where the next wave begins. Why don't we call this a single wave, the first lump or hump? My hump, my love you sinusoidal hump. Because there are 3 zero crossings here where the wave falls to zero. You'd think it would be a great place to identify a whole wave, but there's something very different about the zero crossing here and the zero crossing on the far left and the far right. The ones on the far left and the far right, not only is the wave crossing zero, but if you're plotting it, this is a positive slope here. The local slope of the wave there and over here at time 6 are positive slopes, where in between the other zero crossing, yes, the height of the wave is zero, but it's on its way down. It's a negative slope. So we pick two spots on a wave that have the same amplitude, the same height up and down on the wave, but they also have to have the same slope going on. And in this case, it's the first and third zero crossing that you use. You can also go peak to peak, trough to trough to locate your wave. The length of a single wave is called its wavelength. I know that hardly makes sense at all. And a wavelength is shown by the Greek letter lambda. And lambda is our L, but it's much younger than our L. So lambda is the young L, and the old L is lambda when it got old, and its arches broke, so it went flat-footed. So you can sort of see where our lambda came from. The lambda shown here from Google Docs is like, I don't know, it looks like some Western like Stetson, just like, yeah, I'm trying to rustle up my lambdas. And the height of the wave, right, to the peak right here, is called amplitude. You would know amplitude in plain English as volume. period versus wavelength. Many textbooks, many websites start to confuse you on the sine wave because they don't really make it clear whether they're doing distance or time on the wave, and the plots change. I don't mean the plot as in like, what's the wave going to do next? No, in this case, you could call it the wavelength because you're measuring it at a frozen moment in time. So the numbers 2, 4, and 6 could be perceived as meters. But we also might be plotting it in time. If the wave is moving, the same wave that we just labeled with its wavelength, now the x-axis is in units of time. And, oh, Foolio, you crazy nut, get out of here. This would be a time axis, not a distance axis. This could be something that's changing, like the little heart monitor in the hospital going beep, 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 beep. So which is it? Well, it can be either, and the textbooks and the websites don't make it quite clear what that x-axis is functioning as, and they'll swap back and forth. I can find diagrams where literally they've labeled it as time and wavelength at different points on the same drawing. So you think you're going crazy. The question is this wave a period of 6 seconds, or is it a wavelength of 6 meters? Is it possible that it's both? So once again, it's your understanding that's more important than the math, to know clearly what is being displayed and what is being asked of you. And I will try to make that as clear as possible, but you will see it improperly labeled all over the internet. And as long as you know in your head it could be time or it could be distance displayed on the x-axis, then you will figure out what was really being shown to you, even if the creator of the diagram was vague in terms of what it was they were drawing. What about period versus frequency? Frequency, we talk about the number of waves per second that go by you. So we're not dealing with the time for one wave, but we do a timing of 1 second and see how long before those waves pass you. Once again, we'll look at this as time on the x-axis, not distance. And if I say to you a single wave, crest to crest, trough to trough, or zero crossing to zero crossing, the period of this wave is 0.2 seconds, meaning a single wave takes 0.2 seconds. So how many waves would occur in 1 second? That would be 5. Why did I write period with a nice big bold T with a little serifs, those little hangy sort of east troughs on the end? And frequency is a lovely script F. Tradition. Time for period is always a big capital T. And unfortunately, that is also tension in Newton's law problems. Try to make sure you use period as a nice big bold capital T, and try to give your F a real good flourish on it to make certain you know its frequency. So 5 waves per second is the same as saying a single wave takes 0.2 seconds. This means that period and frequency are reciprocals of each other. Please do not write F is equal to 1 over T as well. Relationship is implied. It's not 2 formulas, it's just one, and it's not even really one. It's just the idea. Frequency and period are reciprocals. When you compute period, you are counting the time of a single wave. The frequency counts the number of waves per second. If 10 waves take 4 seconds to pass you, then the frequency is 10 waves over 4 seconds equals 2.5 waves per second. The period in such a thing would be the opposite, 4 over 10. Notice I wrote 2.5 per second. Its number of waves per second. Its units will be per second. What do you mean per second? whatever you're counting per second. 10 dribbles of the basketball per second, 10 wags of the dog's tail per second, 10 flashes of the car's turning signal per second. It seems odd to say per second, or waves per second might sound better, but the real units is simply per second. Originally they named them cycles per second because a wave is a repeating cycle. Then they finally decided to honor a man named Hertz, who has nothing to do with a rent-a-car or injuring people. And when they say 101.3 megahertz on your FM dial, they're saying to you, you've tuned into a radio wave that is pulsating 101.3 million times every second. Compare that to middle A on the piano, which is pulsating 440 times per second. It is one of the dumbest short forms ever invented. Per second can be written HZ. Get used to it. It's a unit you're expected to know, but it is the simplest derived unit of all. Way simpler than a Newton or a joule or a watt. How do we do this on our calculator? How do we reciprocate these two numbers? There are two keys on most calculators, the 1 over x key or the x to the minus 1 key, and that will create the reciprocal of any number you want. Save you a bit of time. If your calculator doesn't have a reciprocal key because it actually thinks you're smart, it just leaves you with that x to the y key. So I could reciprocal 2.5 by either typing in 2.5 and hitting the reciprocal key, or typing in 2.5, hitting x to the y, and then -1, and you will flip the number. If you are uncertain what the key is going to do, then give it a try. The reciprocal of 2 is 1/2. So if you're not certain if the key is going to reciprocal the number for you, try it with one you can do the answer in your head. Press 2, hit the key. If you get 0.5 as the answer, you're like, yay, it's a reciprocal. If you hit 2 and press the key and you get 1.793, you go, oops, that's not right. How do we plot these waves on a graphing program like Desmos? In grade 12, you will start a thing called radian measures. And this is actually quite easy to do, and you will not believe you ever used degrees once upon a time. I do not want to teach you radian measure. I just want to teach you to plot the function y equals sine theta. Most of you, though, on a calculator or graphing program or on your own would rather write y equals sine x. And this causes confusion because x could be the angle you're plotting. That angle could be represented by time, or it could be represented by distance. So you may see y equals sine t, y equals sine x, and y equals sine theta written. And this up here, if we look at the adjacent and opposite of that triangle, you might be calling them the x and the y, but in reality, the graphing program is assuming the x value you put in for sine is an angle. And suddenly your brain is massively confused because you're going, how can I get the sine of a distance on the x-axis? And it's like, the sine function doesn't care what you called the letter. It's operating on an angle. And it's this problem that you should be writing y equals sine theta, and that teachers get lazy and math programs get lazy and let you type in y equals sine x. You lose track of what it was you were actually doing. You know the circumference of a circle is 2 pi r. That is 360 degrees. So instead of saying to you, I want you to look around 360 degrees, I could say, I want you to look around 2 pi r in all directions. And we can even skip the r because it doesn't matter how big the circle is if you spin all the way around 2 pi. So instead of saying turn around 360 degrees, I can just say turn around 2 pi. A half a circle is 180 degrees. With the circumference formula, that would just be pi r. So radians are like degrees, but they go from 0 to 2 pi, not 0 to 360. Here would be an example to put it all together. A 360 degree circle would have a circumference of 2 pi r. Ignoring the size of the circle, since this formula works no matter what r value you put in, we say the circle has 2 pi radians instead of 360 degrees. That means a half circle, whose circumference would be pi r, has pi radians, and so forth. 90 degrees would be the circumference formula divided by 4. Leaves you pi over 2 r. So a 90 degrees is pi over 2 radians. And finally, if we wanted to do 60 degrees, we'd realize that 60 degrees is 1/6 of a circle. So we take 2 pi r and divide it by 6. The 60 degree circle has 2 pi over 6 radians. I am not teaching this to you to make you use it. I'm just trying to get you to understand there's a different way of putting these numbers into Desmos, and you'll see why in just a moment. When you go to plot trig on your calculator, you can choose whether to report it in degrees, gradians, or radians. DRG stands for deg, rad, grad. Degrees, radians, gradients. Some calculators actually will have the deg, rad, grad on there. If you're in deg mode, degree mode, then you get 360 degrees, goes into your trig functions. If you're in radian mode, it goes from 0 to 2 pi, and if you're in gradient mode, it goes from 0 to 400 degrees. And you will never use it unless you move to Belgium and become a road engineer. It was an attempt during the French Revolution to try to metricize everything. They even planned a day of 10 hours, 100 minutes, 100 seconds. And people are just like, no, leave it alone, leave it alone. So we've stuck with our Babylonian circle of 360 degrees. But you will find by first year university, you have totally given up degrees and you've moved into radians because it's the easiest way to work. On Desmos, if you click the wrench, you will see the choice between radians and degrees. And these programs will almost always show up in radian mode. If your calculator is doing really weird things with trig that you don't understand, like you put in sine 90 and instead of getting a nice 1, you get some weird fraction, your calculator was in radian mode. Here's what happens if you plot the function y equals sine x in the two modes. If you're in radian mode, you can see the sine function peaks at 1, but when it hits 0, you're like, it's literally crosses 0 line at 3.14. And it comes back up at the 0 line at 6.28, exactly 2 pi. There's your full cycle. In degree mode, it'll come back to 0 at 360 degrees. Either way, it's kind of annoying to measure wavelength and frequency since this wave never lands on a unit value. It doesn't do something nice like go 0 to 3 to 6. And this is why I'm teaching you a bit on how to plot with radian mode. Not understand it and explain it, just force the waves to cross at a nice even number so your mathematics is a lot easier. And here's how we do it. On Desmos, in radian mode, it's going to show 0 crossings on multiples of pi. There's 2 pi, there's 1 pi, and in between, there's half of a pi and 3/2 of a pi. That's why the plot's crossing at these weird multiples. You're looking at pi and its fractions. So instead of plotting y equals sine t, we just make a slight shift. If we put in 2 pi for the full circle, then you can treat this subscript here as a fraction of the circle. All right? By the time t equals 6, this whole thing will become 2 pi, a full circle. So this will tell you how many units your circle will be. Now look what happened. 0, 3, 6. So if you leave Desmos in radian mode and you put 2 pi in here, you literally type 2 and then type the letters pi and it will fill it in. And now your fraction underneath here is how long the trig function displays, so you can force it. So if I said to you, what is the period of this wave? You can look and go, 6 seconds. If I said this is a wavelength, you can look at it and go, 6 meters. That's why I'm just pushing in the radian measure here. So you can get nice looking sine waves and work with them a lot faster than if I just let you have them crossing at all sorts of weird values. So you see what I mean? 2 pi t over 6 guarantees one wave will unfold in a unit of 6 steps. And that makes it a lot easier to draw nice, neat waves and count them. Now I want you to go into Desmos and try typing in exactly that. Y equals sine 2 pi. Type that literally in, 2 pi-t. And as soon as you type in the letters pi for pi, it'll pop in pi. T divide by 6. I spaced it all out for you. Just type it in as a single smeared sentence. SIN bracket 2PIT/6, close the bracket, and it knows exactly what you're doing. It's a really nice program that way. And then you can just go in and edit that bottom number and give it a try and see what it does to the wavelength. And then you will have a practical approach of graphing these sine waves, which will make all the old assignments in sound go tons of times faster. Now I want you to play. I want you to make the equation as general as you can. So look at the example at the bottom of the page. Y equals 10 sine 2 pi t over 7. Make sure you set up your brackets correctly and a plus 5. These are the only 3 things you could do to this equation effectively. A multiplier out front that I called A for amplitude, and you'll see what that does if you switch that multiplier from 10 to 3 to 1. Then take your 2 pi t inside, and with this big T underneath, I wrote, just put in a number for there and change it. Then I want you to change and add a value on the end, plus 5, minus 3, plus 2, whatever. Do it for about 10 minutes using this exact equation here, except where the A, the T, and the B are. You're going to just put in pretend numbers and change them a couple times and see what it does to the graph. This is the kind of stuff that used to take me and students in the past like 3 to 4 hours to do. So I would only do like one example. Now you can rip through this in no time in Desmos. Then I want you to plot these 3. And I want you to pay attention to the difference I've given you in the 3 formulas and what it actually does. Once you've done all 3, and you've satisfied yourself what the plus is doing and what the divide by 1, 2, or 4 is doing, and you can change them. You could change this 2 to a 6, you could change this 2 to a 25, but put in 3 formulas simultaneously and it should graph them, and you'll realize what this is doing here. Then I want you to take this little t here on just this upper one, and I want you to change it to bracket t plus 0.1. I want you to take just this t and do bracket t plus 0.1 end bracket. So it'll be inside a double bracket. Then I want you to play t plus 0.1, 0.2, 0.3, t minus 0.1, and watch what it does to the wave. This is how you can learn a lot on formulas. You don't wait for someone to formally teach you it. You just take the formula and start screwing around with the numbers and watch what it does. That way, if you forget a long time later and you go, I don't remember which one of these numbers if I alter moves the formula up or down the page, then try and see what it does. Like, the graphing is done instantaneously, so it's really easy. Then, on those 3 equations from the last screen, I want you to add a 4th equation. If you are clever, all you need to do is copy and paste the 3 original equations into a 4th one, just simply putting plus signs in between. And now we're adding up the 3 separate waves. Scientists like to make things deliberately confusing. When we add vectors, we call it getting the resultant, not the addition. And of course, with waves, they decided, why would we call it the addition of waves when we can make them a new term? And so the addition of waves is called the superposition of waves, which simply means putting them on top of each other. You may have heard the term superimposed image, which is an example to the right, or you took two pictures and you layered them on top of each other. Once you make this combination wave and you see what the addition of the three waves looks like, I want you to go to the additive synthesis link below. It's also like you can't click on a link in the video. You have to go to the actual slideshow or the classroom links to find this one, and go to the additive synthesis one, and you will be able to move the sliders up and down to play with that. So here's what the additive synthesis sound machine looks like. It starts off with a sine wave. That's H1. H2, H3, H4 are new waves at a higher frequency. But in music, these are very specific waves. They are called the harmonics. And the harmonics, if you've ever played music, they're really simple. If you start on letter C, the first harmonic is G. The second one is the next C. So it just goes C, G, C, G, C, G on the way up. And you can slide these up and watch what happens when the waves are added and what it sounds like to your ears as you add these different harmonics. With a very careful application of these sliders, you can make a wave look like a triangle, a sawtooth, a trapezium, a square wave. So the person has set up presets for you to try. It starts off at middle A. You can slide it down. You can change your volume. You can switch these from sine to cosine, and you can switch them from positive, meaning they're adding that sound, or negative, taking it away. You should be able then to see what Desmos was doing, except now you're hearing it as well. Totally not a testing term. Okay, but I did this stuff when I was in grade 7 because I wanted to get my shortwave radio license. And so I went through all this stuff then. So it's easily doable for you, but not testable. You may have heard of the term carrier wave at some point. This is where a wave or signal is sculpted by another one. Typically, a low frequency wave sculpts a much higher frequency wave. When you tune into a radio station, you are turning into the carrier wave. And this is basically how AM radio work. And you're probably going to go, what's radio? Right? Because you've got everything all like downloaded on your iPods or whatever the things are called. I don't know, all that newfangled stuff. When I was a kid, we had to actually go to a place and sit down in front of the music player and not move. If you multiply two waves together, and you got to get your brackets right, it's easy to figure out, just multiply two sine waves together. Start with 10 and 0.2. What you'll see is the 0.2 has many, many, many waves per second, and the 10 is very spread out. The 0.2 becomes the carrier wave. Lots of little oscillations, and the 10 is the big giant sculpting of the overall wave. So try this one out, see what it looks like. Then I want you to add these two equations to the previous one, meaning just click plus on Desmos and add these two. It's literally the envelope wave plotted separately from the total wave. Here we have the envelope times the carrier wave. And here you've got the envelope wave and it's negative. And what that should do is now outline the shape of that envelope wave onto the carrier. Now we're going to shove it out of the way so you can get an idea of what this looks like. I want you then, after you've seen the envelope tracking the real wave and how the real wave was carved to follow that envelope, I want you to slide the envelope down the page. So you'll just alter these two equations with a -5. Now you have your envelope underneath so you can see what the shape of the original envelope wave was and how that little busy carrier wave is mimicking it in outline. Finally, once you have these three equations displayed, you'll have your envelope and carrier wave put together as one function, and then you'll have these two waves plotted as well. And the -5 means they won't be plotted on top of this one. We've moved them out of the way. Now I want you to play around with this 0.2, and I want you to start changing the numbers, and you will see which number makes the carrier wave more detailed as it carves out the envelope? Which of it mimics better? And then which of them would then sound better as a mimic of the original wave? So you've got the shape of your envelope. When you change this 0.2 to 20, does this finished wave look at all like the envelope now, or has it been distorted? If you put the number really tiny, does this envelope and carrier wave look at all like the envelope alone, or is it all distorted? If we think about it, 2 pi t, one cycle is when this number comes back to 2 pi. So the lower number here is actually the period of the wave. In other words, do you want the carrier wave to have a very short period and repeat a lot, or do you want to have a very long period to sculpt out the envelope wave? And this is how you can see, what do you need for a carrier wave? High frequency channels or low frequency channels give you the best copying audio result. And I'll take it up later, but it's far better for you to learn this by playing, because then you can play in the future. You won't remember the answer, but you'll remember techniques of going, I know what to do now. And that lasts far beyond me telling you how to do this by memory. And here are your links that you want to follow on this one to be able to play with these things. And trust me, you go through these websites, by the time you're done, you'll really have a really good idea of doing these waves without plodding through boring textbook questions.